Okay, so I first welcome the students to this course on probability and random variables. My name is Mrityunjay Chakraborty. I am a faculty member at the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur. Well, purpose of today's lecture will be very general. I will first give you an overview of the top of the course, okay, and that itself will be somewhat vast, and having done that, I will devote the remaining time to introduce the students to the concept of probability, okay, from an axiomatic point of view. As regards to the overview of this course, we will first start with probability. Okay, we will first start with probability. We will have this topic. Actually, probability is often defined in common practice, from a frequency interpretation point of view, that is, you just have so many trials and and you observe a particular thing so many times, and just based on that you talk of some kind of estimate of a chance of occurrence and all that. But a theory of probability requires much more than that. It needs what we call axiomatic definition, okay, and that definition relies on set theory concepts. Okay, so I will deal with that and thereby develop the idea of probability, and then that will actually involve some important concept called probability space. And after having developed the notion of probability, I will take you to another very important topic, that is called conditional probability. Okay. After having done that, I will cover random variable or random variable, or means one random variable. So, I will introduce the concept of a random variable. Okay, there will be general this thing description. Okay, and motivation will be to take you to these important notions like probability density function of a random variable and probability distribution. Okay, and then conditional density, conditional distribution. In that connection, there is something else called Bayes theorem. Okay. And Bayes theorem can be used to find out the total probability. Okay. So, that will be covered in this topic of random variable. All right. Next topic will be function of a random variable. Often you do not only deal with the particular random variable in question, but sometimes you evaluate some functions, maybe real valued function, maybe complex valued function, a function of that random variable. So, even if you talk about the probability density, probability distribution and things like that for that random variable, how to have the similar concepts for not the random variable, but its function. Okay. Like what will be the probability density function for a function of a random variable? The function will be given. Okay. Once you do that, that will help you to talk of some very important topics called moments. Moment means, you raise the random variable, maybe the random variable is a real valued random variable, to make life simple. You raise it to some power, say power p, where p is an integer, and take its average. That will be called pth order moment. Okay. So, these moments are very important. At least you can understand that for first order moment, what we get is a very useful quantity. It is called mean, and for second order moment, it leads to something called variance and then correlation and things like that. Okay. So, all these can be covered by using the concepts that come under this function of a random variable. Okay. Then there is something very important called characteristic function. Given a random variable of some particular probability density function, there is some function actually is related to the Fourier transform of the probability density, and that is called characteristic function. That characteristic function can be used to find out probability density of a set of random variables. Okay. Maybe say random variables, n number of different random variables are summed, what will be the probability density of the sum. Okay. So, that is for this function of one random variable. This will take us to the concept of two random variables. Okay. Actually, whenever you have got one random variable, you describe its statistical behavior by finding out its probability density and things like that. Alternatively, it can be shown that you can describe it completely by specifying all its moments, first order moment, second order moment, third order moment, and like that. But that's fine as far as one random variable is concerned. But often in practice, in real life, you will find that there are many parameters related to a particular system or a process or an operation which are random, but they have their mutual relation also. They are mutually dependent on each other, mutually related to each other and all. In that case, you often face a situation where you have to take into account the entire set of the random parameters or random variables and not just one, because behavior of one is not governed by itself alone, but governed by other random variables which are related to it. Okay. So, naturally, in this case what we talk of is not single statistics, but joint statistics. Joint means collecting all of them together. Now, as a first step towards that, we will then consider case of two random variables. That is, suppose there are two random variables x and y. So far we discussed earlier the probability density and distribution of a particular random variable, single random variable. Same concepts will now be extended to the case of joint random variable. Okay. Now, of course, I forgot to mention that when I discuss this concept of a random variable and all that, and especially I discussed this probability density and distribution and all that, I will be basically also presenting some very useful density functions which we come across frequently in life, or even if we don't come across in life, they turn out to be very useful in modeling phenomenon. One of them is Gaussian density. Then there is something called Rayleigh density, there is something called Poisson density, and uniform, of course, is very simple, and things like that. Okay. When I come to this two random variables, I will again extend those univariate, we call it univariate densities, say univariate Gaussian density to a bivariate. Bivariate means when you have got two random variables, okay, to bivariate density. Okay. So, those examples will then be extended to the two variable case. And again, we will have to also define function of two random variables. Like earlier, I have taken here function of one single random variable. It can so happen that your system has two random variables mutually related, and you are evaluating some function, okay, based on both. Okay. For instance, suppose there is a school and there are students. You are finding out age of the student, that is random because that varies from person to person, and maybe the IQ level of student, that also varies from person to person, but they are somewhat related. Naturally, a 5-year-old kid will not have the same IQ as a 20-year-old student, right? Okay. But based on these two parameters, evaluate some function, and that function has some numerical value. So, I will call it a function of two random variables. Okay. So, again, whatever we have done for function of one random variable, we have to do that for function of two random variables, that is finding out the density, probability density function for this basically. Now, after we do all this, there are certain topics, not particularly for a particular chapter of the book, but certain selected topics from various chapters which I feel are important and will be covered. That is, earlier we discussed moments, okay, first order, second order and so on for a single variable. We have to do it for the joint case also. There is joint moment and similarly joint characteristic function, okay. And this will also be useful to introduce you to the concept of mean square estimation, which I will deal with later. Okay, there is something called Hilbert space or other vector space treatment of random variables, which is basically a geometric, which gives you a geometric interpretation of the whole process of estimation. That will be developed there. I will also touch upon another topic called random sequence. That is, a sequence of random variables is coming. Okay, I will just touch upon, because that itself is a very extensive subject, and in that context what is important is this notion of stochastic convergence. That is, we know that any sequence can be converging or diverging. If it converges to a limit under some condition. Okay, there is something called Cauchy condition, and there are many things we have studied. Okay, there are converging tests also. Okay, but when it comes to random sequence, convergence notion have to be defined, because if the particular sequence is not important, the class of sequences, they should converge to a point. So that leads us to stochastic convergence. That is very important. Okay, so I will touch upon these topics. After this, so I just mention them here because I am writing. I will consider this joint okay. And the other topic is, that was number 5 I suppose, right? Yeah. The other topic is number 6 is random sequence. That is what I just mentioned last. Okay. So far, whatever you have covered, up till now, I mean under this plan, of course, we have not covered anything, that is a different matter, but under this plan, whatever we have touched upon, they basically relate to first probability notion, then probability density and all that, and then takes you to individual random variables. Mostly we are considering continuous valued random variables, but the concepts can be easily extended to discrete valued random variables also. Those are called discrete random variables. Okay, that also will be done. But after having done this, we have to extend this concept of randomness, random variables, to something called random process. Random process means we will be now considering waveforms which are random, not just a variable, waveforms. And waveforms could be either a continuous waveform or could be discrete sequence. Okay, that leads to the concept of random process, because it is random process which you finally come across in life. Okay, any observation that you take, especially in engineering, that is over some period of time. So you have a waveform, and that waveform can vary from experiment to experiment, from observation to observation. So that is what we have here in the form of random process. So I will be dealing with this topic after this, random process. Here we will first introduce you to the general concepts of random process, and then there is something called a stationary process. Stationary process means randomness is homogeneously distributed along the axis. I mean, it does not have any bias towards a particular location of the time axis. Okay, I mean, we will of course discuss at length when you go into those topics. Okay, that is called stationary process. Again, stationary process is a concept which is often not met in practice, but we take resort to that, because otherwise analyzing things or devising algorithms or processing means becomes very difficult. Okay, and again another concept is related to stationarity, that is called ergodicity. Ergodicity comes from the need, rather I would say, because we often assume the process to be ergodic, because the need is that you may not get several versions of the waveforms in real life. In real time, you are just getting one waveform, and based on that only you have to make estimation. Using the notion of ergodicity, you can still devise your processing algorithms and all that, okay, to process that actually. Okay, I mean, you can then thereby bypass the need of having several versions of several observations of the same waveform to make, say, average or things like that. That requirement can be bypassed. Okay, and then comes this very important topic, that if you pass one such random process, a stationary process, through a system, okay, which is linear and time invariant, both discrete time we will consider and continuous time also, then is the output also stationary? If so, okay, what is the out? We'll verify that. Okay, of course, with this stationarity, certain notions of correlation and things, related things are associated. So those have to be examined both for the input and output, and based on that only, we can come to those inferences. Okay, so basically that will be covered under the heading systems, that is linear time invariant systems with stochastic inputs. Okay. After this comes this topic, spectral analysis. Okay, spectral analysis. In spectral analysis, we will introduce you to the notion of power spectral density, okay, of a random process. So that will, that needs this notion of stationarity, okay, first, and also, why power spectral density? All that questions will be dealt with. Properties of power spectral density will be explained in detail, okay, and then, as I told you that previously, I will be discussing the effect of a linear time invariant system on a random input. That concept will be used to show how you can generate random processes of some particular wave shape. Particular power spectral, a particular shape. Random processes with some particular type of power spectral density, particular shape. Okay, by designing a linear time invariant system. Okay, so that will be considered. I think up till then I will be considering fairly, good amount of material, but still 2 topics I feel I should touch upon as much as possible, but if time permits. One is called estimation of the spectrum, that is spectral estimation Of course, this is subject to the availability of time and all that, and how far we go. Okay. And other one is mean square estimation. Under this, we will be covering topics like linear prediction, smoothing and filtering. Now, I tell you, this topic, spectral analysis, whether spectral estimation and also mean square estimation, they are very huge topics. You can have one full semester course just on mean square estimation. Similarly, for spectrum estimation, there are, books, entirely devoted to these topics. But obviously, there is no scope of getting too much into all this, but I will try to give some flavor of these topics towards the end of this course. Okay, that is my tentative plan, but if I find that, as I go along, if I find that in the context of whatever I have mentioned, I need to inject more input, I need to discuss some more things, then I will introduce them, I will add on, okay, as and when needed. Okay. All right. Book. Though there are many books available, there is one book which I mentioned. It is given here. Okay. I write its name. It's called this is a book published by McGraw-Hill. I am sure there are economy editions available. Okay, this is a very famous book, a book celebrated all over the world, and this particular author is very well known for this particular book. And of course, he has another book which is also equally famous, almost equally famous. It's called Signal Analysis, but that is not being covered here. That is not being considered here. So this is the book. But I again tell you that there are many equivalent books available in the market. So as long as these topics are same topics are covered, any book for that matter will be welcome. All right. Okay. So I now, after having discussed this, let us now talk in general about this idea of probability. Actually, this topic of probability comes in the context of studying some natural phenomena, or maybe some experiments that we carry out, where we find that the outcome of the experiment is not something fixed, but there is something random about it. Okay, that is, if you try to observe the same thing again and again and again, you find that you are not observing the same thing. Okay. For instance, as I told you, suppose you go to a school, a particular class, so a particular class you go to, and then you just ask for the ages, exact ages, year, month, date, number of days, and like that for each student. You will find that no two figures are matching. Okay, for each student, his or her age is something, and for another student again, the age is something else. Even though they are close, because probably in a class, you expect the students to be having age close to each other, but not exactly same. Okay, so here the outcome, which is the age of the students, is varying. Okay. Similarly, suppose there is a chemical process, some process is going on, there is a furnace, and you want to measure the temperature of the furnace or some part of it, okay, every now and then. You find, even if you try to measure, you do not find exactly the same temperature. You find temperature in a certain range could be narrow, but the temperature fluctuates. Okay. In such contexts, and there are many other contexts now you yourself can visualize based on these examples. Now, in such contexts, one nice thing has been observed, that okay, as far as the outcome is concerned, I agree that there is a randomness, there is some unpredictability, there is randomness, you can call it chaos, you can call it anarchy, whatever. But there are certain things which do not vary with time. That is, it has been found experimentally that for each of these experiments, certain averages, if taken over a sufficiently large number of outcomes or observations, they somehow approach some steady value. Okay, and even if your number of observation goes up further and further, these averages do not change. So these averages rather characterize the particular process, particular experiment that is going on. Okay. Further, okay, even if you don't take all the outcomes, suppose outcome 1, outcome 2, outcome 3, outcome 4, and like that, there is a sequence of outcomes. Even if you don't take all the outcomes, but take some subsequence of the outcomes, you will still find that the average, that certain average, that average value remains same. To give you an example, suppose you are tossing a coin, and as you go on tossing a coin, you find out after a while the percentage of the percentage of occurrence of head. Okay, so many trials and so many times I got head. So what is the percentage? You will find that if you toss it several times, then that percentage figure will approach the figure 0.5. If you go on still tossing, you will see that the average will not vary much, around 0.5. It will approach the steady value if your number of observations taken already is huge. All right. Same thing will happen even if you don't take all the tosses. Suppose I take only every fourth toss and see its outcome, and based on those outcomes only I do the average. Even then I will find the percentage of occurrence of head is 0.5. Corresponding percentage. All right. So that led us to this motivation for concept of probability. Now, in the case of probability, classically, if there is any experiment that is going on and you are observing outcomes and total number of observation is capital N, out of which a particular event occurs, particular event say A, that occurs small, I mean these times, n subscript A times, then the corresponding probability is nothing but this. This is a classical definition, it is called frequency interpretation of probability. It gives you a chance of occurrence of A, provided of course n is large, number of observation is large, that okay, I have taken so many samples and out of which so many outcomes, out of which only on NA occasions I got A. So, if capital N is large, then this ratio does not change its value even if you take more and more outcomes. So, that is the classical interpretation of probability, it is called frequency interpretation. So, in practice often it comes to help, but in a theory of probability, we do not rely on this, we try to develop a mathematical definition of probability. Okay. Well, when you have to really estimate from real life data, that time you can take recourse to this, but we want to evaluate its properties, so that we can devise algorithms, we can devise processing means, okay, based on those properties. Okay. That takes us to what is called the axiomatic definition of probability. All right. Now, to get into this, first thing we have to do is to revise the set theoretic concepts, because this axiomatic definition is based on set theoretic notions. So, I will quickly go through this and then maybe I will just take you to the stage of stage where we can formally get into this axiomatic definition, but that detailed discussion on this axiomatic definition of probability we will carry on in the next class. Okay. All right. In set theory, first we have got a set S, and the set S, to start with, it consists of some elements. Okay. Elements are say theta 1, theta 2, dot say theta L. This is a collection of elements. This is a discrete set. Discrete set means it's a countable discrete set. Countable because you can count the total L elements, and discrete because either this or this or this or this. Okay, I start with this sort of set because this is very easy to understand. But this set could be a continuous set. For instance, set could be a segment of the real line between the number 2 and 3, isn't it? And that is not countable. You cannot count the total number of points that you have between 2 and 3. All right. Sometimes a set can be countable but still infinite. This is a finite countable set. This is very easy to understand. Okay. Here or for any set, as you know, I can write theta I element of S. This stands for element. So, it is an element of S. That is, this is a member of this set S. Then there is something called this will be called empty set. Okay. And subset, any subset of S is a collection of the members of the set S. So, each member is a subset. This empty set is a subset. Empty set is a subset because empty set is already a part of it. Empty set is part of any set. So, this is a subset of this. a set consisting of only one element theta 1 is a subset of S. A set consisting of any element theta 2 is again a subset of S, and likewise. Or maybe a set consisting of theta 1 and theta 2 is a subset. Theta 2 and theta 3 again is a subset, and likewise. Okay. If A is a subset of S, we write like this: A is a subset of S. All right. Now, can you tell me, for a set like this, how many subsets in total can you have? 2 to the power L. That's the correct answer. Why? Okay. Yeah, please tell.
Actually, if we are considering individual, then
yeah, actually it's like this. I mean, you start with 1, that is this. Okay, 1. That's for the empty set. Then 1, 1, 1. So L subsets. Then you take 2. So that means how many combinations? LC2. Okay. Then LC3. And like that, up dot dot dot, after that LCL. That will be nothing but a binomial expansion of 1 plus 1 whole to the power L. Sorry, whole to the power L, okay, which is 2 to the power L. Okay. So, I have got so many those many subsets. Okay. For example, I will just take an example from the book, because that is very good in the context of our business. Suppose a coin is tossed twice, okay, and based on those 2 tosses, I have a set S which I write like HH, HT, TH and TT. Here HH stands for that event where both on first and second toss you got heads. Here first you got head, then tail, tail and then head, and both tails. Okay. In that case, I can have a subset, say A, as what is the subset? It is a subset of those events, these are all events, it is subset of those events where at least one head has occurred. Okay. Similarly, I can have another subset. This is a subset where first toss always give you H, and likewise. Okay. All right. That takes us to set operations that I will do in the next page. One is union, okay, given a set A and B, 2 sets A and B, I define union, or sometimes we call it sum of A and B as A plus B. Okay, you are used to this notation A union B, but as I will be going along with this book, I will follow this plus rather than this. This is not arithmetic plus. What does it mean? We all know, but still it is worth repeating, that resulting one is a set where all elements of A and all elements of B are present. Okay. So, if you have a Venn diagram, if you have a Venn diagram like this, suppose this is A and say this is B, then A union B will be this entire stuff. Okay, this is A union B. We call it A sum B also. Okay. Similarly, product or intersection. Okay. This is denoted by B. You can put a dot, but you are possibly used to this notation. Okay. But again, going by the book, I will follow this. This means this intersection is a set where only those elements which are present both in A and B are contained. So, it basically looks at the overlap between A and B. Okay. That is in terms of the Venn diagram. If you have got these to be A and these to be B, then this is your A union B. This part is A intersection B, this part. Okay. The next one, this union and intersection, they satisfy some properties which can be easily seen. That is, coming to union first. Is same as, this is obvious, union of A and B or B and A, they are okay. It's called commutativity. Then other thing is again, no need to draw a Venn diagram for this. This is, this can be easily inferred from common sense. That is, you are taking a bigger set here where all elements of A and B are present, including the overlap. That again you are summing with C. So, resulting thing will contains all elements of A, B, C. Same will be here. This contains all elements of B and C, a bigger set. With that, if you combine A, then again total set will be what? It will consist of all elements of A, B and C. So, that is why both sides are same. All right. Okay. Now, when it comes to this when it comes to product, this relation is pretty simple. You can easily understand what it is. Overlap between A and B or between B and A, they are same. It is just to define sentences. Okay. How about this? Is it same as in fact I am using this intersection, but actually interchangeably I will use it in the product sense also, that is AB. AB is BA and ABC is ABC. Okay.
But these two properties will not hold for union.
Why is holding?
This product.
No, this is associate, na? Like AB with C is same as A product with BC. Similarly, A plus B plus C, these two things are same. This is called associativity. Okay, we can see this just by this Venn diagram. Take again thing like this, A. This is C. In fact, let me use this. Okay. What is the intersection between A and B? There is this entire region. That intersection with C will be what? This part. So, what is A intersection B or A product B and then product with C? That is actually the overlap between A, B and C, the common part, that is this part. Okay. Similarly, if you consider B product C first, that will be this entire region. That intersection with A will be what? Only this. It should be same. Okay. Then comes the other property, which is a combination of both union and intersection. That is I am using this style again. Instead of using the intersection symbol, the product symbol is here, meaning the same thing. This will be again for that we take this. This is A, okay, let me erase it. Let me call it B. This is C. So, B union C is this entire region. That intersection with A. So, suppose your A is this is your A. So, what is A intersection B union with C? B union with C is this entire region. With that A is intersecting, so that means this zone. All right. What is A product with B? That is A intersection B, that is this part. What is A intersection with C? This part. And their union will give you again this. Okay. So, this is actually called distributivity, that is this intersection is distributive over union. Okay. Certain things you can see that A intersection with A will give you A. A intersection with phi will give you what? Phi. Because this is common in this also. Okay. A plus A union with A is A plus phi, here is a difference, that will be A. Okay. In general, if A is a subset of S, then A intersection with S will be A itself, and A plus S will be S. Okay, very elementary things. Few more definitions. Suppose you are given a set S, you are given a set S, you have got two subsets A, B. A and B will be called mutually exclusive if there is no intersection. Okay. Using probabilistic notions, it means that A and B could be two events which cannot occur simultaneously. Just to give an example. Okay. All right. This takes us to concept of partition. Suppose a set S, out of a set S we derive some subsets A1, A2 up to say AN, such that AI, each AI is element of a subset of S, I equal to say 1 dot 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 n, and AI, another thing is they are mutually exclusive. AI AJ is phi, and another property is they are taken such that if you take the union of them, you get S. That is another thing, A1 plus A2 plus dot 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 AN, that is your S. Then this set AIs is called a partition. There is entire set S has been partitioned into smaller subsets, so that no space has been left out. You just unite them by union, you get the entire set S back, and there is no intersection between them. Okay. And last thing is complement of a set. If A is subset of this, then A bar is called the complement. A bar means all elements of S which are not present in A. Okay, that is called complement. So if you take capital S itself, then its complement is empty set, and empty set has its complement equal to the total set S. Okay. So this takes us to, well, before I go into that, maybe we can just quickly tell you this De Morgan's law, which you have already studied, in the context of digital circuits, where again they talk in terms of logic, but again, underlying principle remains same. De Morgan's law is like this, if you take this, you can verify by Venn diagram. I give it as an exercise. Take complement. That is, take the union of A and B, its complement. You can verify by Venn diagram. That will be nothing but intersection between A complement and B complement. and on the other hand, if you take the intersection and then take complement, this will be nothing but sometimes I am using this union, sometimes plus. Okay. So, please do not get confused, because I am more used to this union symbol, and I am sure you also. Okay. These are the two main De Morgan's law. I am not getting into the proof. You can easily do it using set theoretic concepts, using a Venn diagram. Okay. So, this is as much as far as this set theory part is concerned. This will take us to the concept of probability space. I will discuss this at length in the next class, but just to give you an idea about why we dealt with so much of set theory today is that, I will first define some set which is called the probability, which is actually called a space. That space will be the total set, and that will be called the certain event. That is, that will always occur. Some experiment is going on, so that set will represent something which is bound to occur. It is such an event. There is a total set. Each member of that set will be called an experimental outcome. That means the set will consist of all possible outcomes. Therefore, the set is an event which is bound to occur. Those outcomes, you can collect some of the outcomes that form a subset. Each subset will be called an event. So, event can be each of the outcomes, or a combination of the outcomes, or the entire set itself. Okay. And then on that set will be given a set S like that and its subsets. Okay. There we will introduce some measure, some function or measure called probability. Okay. That will be the axiomatic treatment to probability. So, I will be stopping here today. Just to summarize what we have done today is this: we have given first an overview of the entire course, but even though I tried to be exhaustive and to the point there, I added that as I go along, I might introduce certain extra things in each chapter which I have not named today. And after having done that, we have discussed the idea of probability, its need or motivation in general terms, and then we have explained that this classical frequency interpretation based notion of probability alone is not enough, because to take a proper we need to give a proper treatment to this topic, and that takes us to the axiomatic definition, for which set theoretic knowledge is required, because using some sets only we will develop those axioms. Okay. That will reserve for the next class. Okay. So, if you have any questions, fine, otherwise I wind it up. Okay, that is all for today. So, in the previous class, we had first discussed, we have presented this outline of this course. Okay. A detailed outline was given as to what all will be covered, and then I tried to develop the motivation for this theory of probability, okay, in very general terms. And that time I mentioned that this theory will be developed using some solid mathematical foundation of set theory, classical set theory. Okay. And then I discussed the basic set theoretic notions, definitions and operations at length. Today, I will be using those concepts of set theory to first introduce you to the topic of to the subject of probability space, and we will be discussing the properties of probability space, and using this definition and properties, I will then go into what is called axiomatic definition of probability. We will enlist certain axioms, and then we will get into the consequences of those axioms, and then I will try to relate them to real life world, because after all the axioms are purely mathematical. Okay. And then once those axioms are given or described, then I will get into some further sophistications in the form of something called field of sets. In fact, a particular class of fields, particular type of field called Borel field, and in this Borel fields only mathematically we can apply these set theoretic these probabilistic axioms correctly. Okay, so I will go up to that. We will also consider some examples. So, first I start with probability space. First, let there be a set S. This set can be finite, countable, or infinite. Finite and countable are the most, the simplest of all cases. Finite, the total number of entries is finite and countable. It can be infinite but countable. Like I mean, do you know? Can you give an example of such set where the set is infinite but countable? Say set of integers is countable. It's called countable infinite. Or set can be itself non-countable infinite. For a real line. Okay, it can be anything. But for our treatment, I will try to first take those examples where S is finite and countable. Okay, and then we will try to when you try to generalize it to those infinite sets, then only I have to get into that what I said, field of sets and Borel field and all that. Okay, so this set S it consists of experimental outcomes. I will explain. Meaning S is something like E1, E2 dot 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 dot. Now I am constructing a field. If A is present in that field, A bar also must be present. And number 2 is if this should be actually element, because these are now sets are now elements of the class. Class is what? A collection of sets. So each set is an element of the class. So it should be element, not subset. Okay. If then these two. Using this, we will show that this applies also to the intersection. Using these two, we will develop some properties. We will show that if A is an element of F and B is an element of F, then AB also is an element of F. So the next class I take from here, okay, and I get into something called Borel field, and there I give the more exact definitions actually. Okay, Borel field, I will tell you why Borel fields are required. Okay, because when you have got that infinite set, all subsets don't qualify for events, only those which give rise to Borel fields, they qualify for events. Okay. After having done that, I will get into again more practical things, there is a conditional probability and all that. We will solve some problems also. Okay. So that's all for today. Thank you.